Still not able to figure out how to get the largest rectangle in a histogram? Or are you fed up on finding how many braces to add to get a set of parentheses balanced? We have it all covered at Expertifie. Hello, my name is Gary from Expertify, where we try to get you to your dream companies. Expertify offers system design and data structures courses in your favorite programming language. Whether it's designing a logging application or optimizing time complexity for a problem you're stuck on, we have it all covered. This session on stacks will have you set up for success in your upcoming FANG interviews. So stay tuned for the lecture ahead and hope to see you guys in the courses.
Cool. So let's start. Let's start with what are stacks. So stacks, as we know, they are linear data structure, and the order of storage in a stack are of two types: LIFO, which we call as last in first out, and first in last out. Like both are the same thing. So let's see what are some basic stack operations. So just to remind you, like I will cover the basics in very small time. The main agenda is solving Google level of interview questions. And yeah, so just brushing up the important points before we jump right into the problems. Okay, so there are following operations which we do on stacks, which are push, pop, is empty, and peek. Peek is also known as top in quite a few languages. So what are really these operations? So let's go into a little bit of brief about each one of them. So push operation, this is basically inserts element at top of the stack. If we try to push an element in an already full stack, then an overflow condition can occur. This can happen if your memory is out of bound. Stacks don't have a static memory allocation. You can keep adding elements on top of the stack, but if the memory is completely full, then you get a stack overflow. This operation takes order of one time. And this is one such example, that your stack is empty, then you push one element, you push another element, then you push 6, 8, 10. And after this, if the memory is full, then we will have what is called as stack overflow. So important point to note here is that elements are pushed on top of a stack every time. Okay, so every element is being pushed on top of it. And let's move to the pop. So pop removes an element again from the top of the stack. And this also is order of one operation. And let's see diagrammatically. So in the same stack, if I pop, now 10 will pop first, then 8 will pop, then 6 will pop, then 4 gets popped, and then 2 gets popped. And if a stack is empty, you can't pop anymore. So that's stack underflow. So these are some basic stack operations. Push and pop both are done in order of one time. Okay, so quick reminder on these push and pop operations. Let's move to other two important operations which are there. One is empty, which tells if the stack is empty or not. And the another one is top, which tells me what element is at the top of the stack. Okay, so a quick diagrammatic explanation of top. So if this is the stack, then top of the stack is the top element, right? 2 is the top element here. In this case, 1 is the top element. If you pop 1 from the stack, then again the top element becomes 2, right? So these are some quick reminders on what are stacks. Okay, so before moving forward, let's have a quiz. So I will launch a quiz. Let me know if you guys are able to see it. So the question is, what data structure would be the best to implement a stack? And your options are a singly linked list, a doubly linked list, arrays, or lists/array lists. So given these 4 operations, push, pop, is empty, and top, which data structure would suit best to implement a stack. Remember, stack is a dynamic data structure. There is no size of a stack. We don't pre-allocate a size. We keep pushing elements on top of it. And when we have to pop, we also pop from top of it. So the only way you can insert or remove from a stack is from the pop. So from the top. Okay. So considering this, what would be the correct answer? What data structure would you use internally to implement a stack? Stack in itself is a data structure, but how do you implement a stack if you had to? Generally, people use STLs for stack. So let me firstly check if there are some questions. Okay, singly linked list. So a lot of people, majority of them are saying singly linked list. A few of them doubly linked list. Some are saying less. Answer can be any of them, but the best data structure which would be good in implementing is singly linked list. And we won't go much into detail of how, because that will again be a 101 on stacks. But we are here to solve some problems, and there are stack library available in all the languages that you use. In C++, there is stack STL. In Java, there are collections, and similarly in other languages. But the correct answer for this is singly linked list. And we can have future sessions on going into detail about how each of these approaches compare against each other and why singly linked list is the best possible way to implement a stack. Okay, so let's move forward. Okay, so let's start with the first very widely known problem, which is solved using a stack, right? Which is balancing parentheses. So the question is that given a string, write a program to examine whether the braces, which can be a curly brace, a small brace, or a square brace, are balanced. Okay. And just to give you some example, so this is one sample input, which is not balanced clearly, right? And another input, which is also not balanced. Why input 2 is not balanced? Because we started with a curly brace, then we opened a square brace. So far, so good. Then we opened a small brace. Again, so far, so good. But we closed the curly brace first. We can't close the curly brace before we can close the small brace and the square brace, right? And if you carefully observe, then this means that elements, the behavior in which a balancing of parentheses happen, we close the brace first, which has occurred the last. Like if this curly brace, before this curly brace, we wanted a small brace to close and then a square brace to close, and then this would this expression would have been valid. But at this point itself, when a curly brace came, this is an invalid expression. So basically, what do we let's see some positive examples before we move ahead. So these are positive examples, like you opened a square brace, then a small brace, again opened a small brace, so far so good. But when you closed a small brace, that is also good, because the earliest opened, the last opened brace was a small brace. Again, you open a curly brace, again fine, again fine. So this follows your balancing property, okay? That the last brace that you have opened has to be closed first, and so on. So if you see, the first brace was a square brace and it has been closed at the end. Similarly, for others as well. So this is a property which balancing of parentheses holds. Okay, and again, a negative example is there. So we'll talk into a lot of detail about how balancing of parentheses work, but there are two things which we should keep in mind: that open brackets must be closed by the same type of bracket, okay, like we all know, and the closing open brackets must be closed in correct order, which we are talking about. So these both things are important in balancing of parentheses. And let's see how we solve this using a stack. So using a stack, let's say this is your expression, a string, okay? And initially your stack is empty. So firstly, you get a square brace. So you push a square brace. Open brace will always be pushed on your stack. So this is the approach. So you push, open a square brace, open any type of open brace, you will push on the stack. Then you get a curly brace. Again, you push that on stack. Then you get a small brace, that also you push onto the stack. So far, so good. And now you get a closing a small brace. Here you need to see what's at top of your stack. If the top of your stack is an opening brace, small, same type of opening brace. So you have a small closing brace. So the top of your stack has to be a small opening brace. If that's the case, then it's good. So you can pop that entry out of your stack because it has already been balanced by a closing brace. Next, you get a curly brace. Again, you see at top of a stack, now your top of your stack is a curly brace because you popped the element on the top of a stack in step 3. And now since they match, you again pop this. And at the end, again, you pop when a square brace comes. So at the end of 5 steps, you will see that your stack is empty and you have traversed all the elements in your string. If this happens, then we say that the parenthesis is balanced. Okay. So this is how, using a stack, you would solve this problem. Any questions on this? Any doubts, any clarifications before I move ahead? Okay. So this is a very trivial problem, right? So we are starting with this first. And as usual, we will actually see the implementation of this. So let me reset to default code definition. Okay, so now as we have discussed, right? So what are the steps? So step number 1 is that if open brace, then insert in stack, right? Step number 2 is that if not open or if close brace, then you need to evaluate 2 things. Firstly, you see if what is at top of your stack, right? And the element that is at top of a stack, is it a matching brace to this close brace, right? So before you see what is at top of a stack, you need to see if your stack is even empty. Like, what if your stack is empty and you get a closing brace is the first thing in your input? For example, what if the input was a single character, which is a closing brace, right? Then you have nothing on your stack and you get a close brace. There is nothing at top of your stack as well. So if the stack is empty, then you know that you have a closing brace which has no opening brace to match it. So that means this is not valid. That's the first condition. Second condition, if it is not empty, then you evaluate the top of a stack and you check if it is matching to this brace. And if it is, in a way, we can say if it is not matching, then we will again return false. And if you did not return false in your step 1 and 2, then you say that yes. Then you still don't say it is true, right? You wait for your entire string to be processed. And in step number 3 here, you will say, if you processed all your braces with an empty stack in the end, then the parenthesis is balanced, right? So this is your algorithm. Let's take a corner case and evaluate if we are doing, if what we are saying is correct. So let's say this is a example of clearly this is invalid, right? So what would happen? So we would firstly have a stack, right? So let's say this is our stack. So in our stack, whenever an open brace comes, we will insert, right? So we get this. Firstly, we are processing this. We insert this in our stack. Next element is a open small brace. So again, we insert it to our stack. Next is a closing a small brace. So our top of the stack is a opening small brace. So they both match, right? And our stack is not empty. So far, so good. So we process further. Now the next element is a closing square bracket. But our top of stack is also opening a square bracket. So again, we are good. Now our stack is empty. But the next expression is opening a small brace. So again, we push this to our stack. So we will exit with our code very happy, but we will fail because the stack is not empty in the end. Okay. So now hopefully all the 3 steps make sense. And now we will quickly program this with whatever logic we have written here. We will use the stack STL. And inside the stack, what are we storing? We are storing these characters. So this is a stack of characters, stack character st, and then we will iterate through the input. How will I iterate through the input? I'll just scan it. Okay, so I scan through it, and the first thing I check is if this is an open bracket. So I'll have a function for that. And I will see if this character is an open bracket or not. If this is an open bracket, then what do? I simply push. So I will do a stack.push. Now here is the else part. If it is not an open bracket, then the only possible characters, because in this question, are open and close. So we can say if it is not an open bracket, then it has to be a closing bracket, right? And this is open bracket will take care of all the three types of braces that are there. So that's why I have made it as a method, which I will define here is open bracket, right? I'll just quickly define this, and this will take a character C, and it will evaluate if this C is equal to either this or C is equal to this, or this character is equal to this, then we return true, otherwise we return false. So this is our simple is open bracket. And this I will take it out of this method and actually paste it in. Okay. So now in the else part, like we discussed, now we have to check two things. If we get a closing brace and our stack is empty. So if stack is empty at here, then we terminate our code right here and we say this is false. It can't be valid because you got a closing brace and you have nothing to balance it with. But if it is not empty, which would happen, if it is empty, it would simply return here. So now this is your else part. If this is not empty, then you go to the stack top, right? And you see if the stack top is matching. So we will have a function for this is matching brace. And we will compare the top, which is the opening brace, with the current input, which is the closing brace, right? And if it is matching, then we are good. But if it is not matching, this is the part we would be concerned with. If it is not matching, we will again terminate our code here, saying this is false. And now we'll and after this, of course, stack.pop, right? If it is a matching brace, if the stack is not empty, then you actually pop the opening brace from the stack. And after all of this, remember step number 3, we still need to check at the end of our input if our stack is empty or not. So again here, if our stack is still not empty, then again we return false. Otherwise, we simply return. Okay. And now I just need to write this small method is matching brace. And his matching brace is as simple as, what is a matching brace? It will take two characters, right? One will be open, one will be close. And how will they be matching? There are only 3 possible ways, right? If open is equal to opening bracket and right, close is equal to closing bracket, then this is a matching brace. Or if open, and I'll copy paste this. If this is a square bracket opening, then it should close with a square bracket. If it's a curly bracket, then it should close with a curly bracket. So if the open and close are this, then they are matching, right? So in this case, we will return true. Otherwise, we'll return right. So if this is our matching criteria, and now let's see if there are any compiler errors or something in our code. Just run this code. And let's try on some innovative inputs. This should be not balanced. Let's see if you return the correct answer here. Yes, so I'll just submit this. And this got accepted. Okay, so this is balancing parentheses. So any questions so far? Quick roundup of the class. Any questions on this problem, balancing parentheses? Right, so it was very simple. You have a stack and you have 4 steps. If this is opening brace, you insert it in the stack. If it is a closing brace, then there are 2 conditions. You need to see if the stack is empty and a closing brace is there, then clearly there is no matching brace. Then you return false. If the stack is not empty and the top of the stack is not a matching brace, let's say you get a small closing bracket and the top of the stack is the opening curly bracket, then that is also a mismatch. Then again you return false. After traversing the entire string, still if your stack is not empty, which means there are some closing braces which have been missed, there are some extra opening braces, then again you return false. And if none of these return false, then this is a valid parenthesis. Okay, so now let's move forward to the next question, which is an advanced version of the first problem. Okay, so before going this, anyone has any doubt in the first question? Should I take that as a yes? And are you guys able to see my screen? And when I was using lead code, were you guys able to see my lead code screen? Can I get a confirmation? Yes. Okay. So now let's come to, now from here, the difficulty level will increase to some non-trivial problems. And this is the first of one. So this is our second modification in balancing of parentheses. So the question is, remove the minimum number of parentheses, okay, which is, just a reminder, this time the parentheses will only be small braces, okay, opening and closing small braces. There are no curly or square brackets. So only one type of brace is there to make the problem simpler. Remove the minimum number of parentheses, which is either an opening or a closing brace, in any position, okay, so that the resulting parenthesis is valid. Let's take some example. So this is a not balanced parenthesis. Why? Because there are 2 opening braces and 3 closing braces. So you need to output me the, after removing, you need to give me the output, which is obviously this is the balanced output, but you could not output, let's say, just 1 opening brace and 1 closing brace. That is also a valid output, but this is not after minimum number of removals. So you need to output me a valid parenthesis after minimum number of removals. So in this case, the number of removal was just 1, right? If I just remove 1 closing brace, then it becomes a valid string, right? Another example is, so braces. So in this question, basically there can be other characters as well, but braces can only be of one type, okay? So let's say lead code is there. So like it's as good as forgetting all the characters. You just need to focus on your braces. Again, it's the same problem like input 1, but here you can see that some random characters are also there. So even if that comes, then as part of this question, you need to only remove 1 character, which is the last closing brace, and return the output. Okay. So you have to output a valid string with least number of removals. Okay. So that's the question. Now this becomes interesting questions. So far we were just outputting yes or no. So there is some question on chat. If we have only opening braces. Oh, that's a great question. So if you have only opening braces, then you have to delete all of them, right? So empty parenthesis is a balanced parenthesis. So if you only have opening braces, then you remove every one of them. That's the only possible way to get a balanced parenthesis. Nice question there. Okay, so again, this problem is picked from lead code, but before going and implementing, I would actually, let me try to explain how we can solve this problem. Okay, so I will use some, let me know if you guys are able to see my screen. Are you guys able to see my screen? Can somebody give me a confirmation? Yes, awesome. Okay. So this is, so let's only focus for firstly for those cases where there are only small braces and no other characters are there, and then characters can come in. We will see that it makes no difference to this problem. So let's say that your first question is this. There are only one type of brace. Okay. So far, how we were solving balancing of parentheses, we had a stack which was empty. And when we get this opening brace, we put it on stack. Again, when we get another opening brace, we again push it on stack, right? And when we get a closing brace, then we look at the top of a stack. And if they are same, we pop. Next closing brace, again, we see the top of the stack. If they are matching, then again we pop. And now you will get a closing brace with no element on the stack. So can I say that at this point I can say to delete this? Yes, I can. Because if I delete this, then this becomes balanced. Because why it becomes balanced? Because till this point, my stack was empty and I got no error. Like there were no inconsistencies, like the stack was empty when a closing brace came, or when a closing brace came, the top of my stack was a non-matching opening brace, right? So I can safely delete whatever is left. But is that minimum number of deletions? Let's figure that out. Let's take another example. Okay, so this is your string. And you know that the correct answer here, what will be the correct answer here? How many deletions you will have to make? You will have to delete this, and you will have to delete this, and your output will be this. So let's see how we can modify our initial method to solve a problem like this. So again, we will have our stack. And we will start from this, and right at the onset, we get an error that we have a closing brace and our stack is empty, which is an erroneous condition. So whenever you get an error, you just delete that brace. Let's make it very simple. So all the error conditions, whenever they, so in the previous problem, whenever error came, you returned false. Here, instead of returning false, you will say that we have to delete this character. Okay. So I say that, okay, delete this. Because this gave me error, I will delete this character, and let's now move to the second character. This is the opening brace. I'm happy. Opening braces are always welcome, unless they are left at the end. Okay. Now we move to the second brace, which is a closing brace. Now this closing brace comes, we look at the top of a stack, matching brace, non-empty, and then we remove this, right? Now comes another opening brace. Again, opening braces are welcome. Now we put this on stack, but we reach the end of our string. And now we see that this stack is not empty. So again, because of this element, I know that error came. So again, because this gave me an error, I will again say delete this. So I'll say delete this. Okay. And now I will be just left with these two, and this will be valid. So now I'm sure that this method will always give me the correct answer, but the question remains that is this minimum number of deletion, right? That remains. And I will answer that intuitively. There is no mathematical proof as such here. The answer here is that whenever you get a mismatch, right, whether it is because of an opening brace or a closing brace, if you remove that, then it doesn't make a difference. For example, like let's say you have this example, right? In this, either I remove this or I remove this. It doesn't really matter, right? What matters is removing one of the closing braces. And because the types of braces are same, so I don't need to worry much. So turns out that this method will always give you the minimum number of removals and always end up in a correct output. Okay. So this is the approach. Let's validate this with a stronger input, which has all sorts of possibility of mistakes. We start with couple of closing braces, then some opening braces, unbalanced closing braces, something like this. And let's see what is the valid output here. So again, we will have our stack. And the first element. So the first element is a closing brace. I say an error has occurred and I say remove this. Second element is again a closing brace. Stack is empty, error. Third element is now a opening brace. I'm happy, I push it to my stack. Second element is again an opening brace. I'm happy, I push it to my stack. Third element is a closing brace. I check the top of stack. I get a match. I'm happy. Third element is a opening brace. Opening braces are always welcome. Fourth, the next element is again opening brace. Again, fine. Next element is again opening brace. Again, fine. Now we get a closing brace. Top of a stack is the opening brace. I'm still okay. But now I see that I have 3 braces inside my stack. And all of these have caused an error. And now I will go back to all of those 3 braces, which were this, and this, or this. It could be, like I said, order doesn't matter. It could have been this, and this. Okay, either one of these 3 you will remove. And let's see, you remove this. And then after your minimum number of deletions, this is your output. And if you had chosen the other path, then this, you wouldn't have removed this. Rather, you would have removed this. Then your output would have been this. Sorry, this is not removed anymore. So you'll get this, then this closing, and then this. Both of these are valid parentheses, and both of these involve how many deletions? 3 here and 2 here. 5 deletions in each. So both of these are correct answer. Now let's go back to the lead code question. Okay. So I will end the poll. I think answer of the first quiz was singly linked list. So let's. And now let me stop sharing my screen and go back to my original screen. Okay. Can somebody confirm? Are you guys able to see my lead code screen? Thumbs up. Yes. Yes. Awesome. Okay. So now let's come to the Canva and let's see how this problem is framed on lead code. Okay, that was some glitch from lead code. Let's open this problem. I may have this. Okay, fine. So same question, given a string of small and open brace and a lot of lower case English characters, your task is to remove minimum number of parentheses in any position so that the resulting parenthesis is valid and return any valid string. Okay. So out of, if there are many possibility, like we did in the last question, return any. Okay. And some explanation of what is a balanced parenthesis, which we already know. And this is the question that I picked. Okay, so lead code, remove firstly all the English characters, and you will end up with one open, one close, and another third close. So now the answer is that you need to remove the last character, which is the last closing brace, and then you will end up with lead code without the last closing brace, and that's a correct answer. But along with this, you could have removed any of the closing braces, right? After O. So that is also a correct answer, right? So that will also be accepted. So now any answer is fine, but it has to be valid and after minimum number of deletions. Now, so why I picked this question? This question is good because it's easy to get the approach, but now comes the challenge of implementation. This is a very implementation heavy problem. Why? So when I say that delete a character, I can say that very easily, but how do you delete a character from a string in order of one time, right? Or like generally, if you delete a character from a string in the middle, then you have to create a new string, right? The strings are generally immutable. Even if you can do it let's take an example of an array. If I want to remove the fifth element, then I will remove the fifth element, and then I have to slide the sixth, seventh, and eighth element back to one place, which takes order of n operation. So that becomes a challenge here, that how do we optimize the time complexity of this problem? So the answer to that is very simple. So I will go through my approach here. I will not code this because this is a little bit implementation heavy. So firstly, I start off with a this is just a vector. So my first statement somewhere here would be, okay, what is this? Minimum remove, right? Yeah. So the first thing that I would do here is that I create a vector of braces and I create a Boolean mark, right? So I use an array to mark which brace I want to delete. So I will mark all the braces with respect to their positions, right? So that's why I have created a vector of pair of char and int. So this will store my brace and the position. So I will break down the problem into only the braces. Okay, I will forget about the the English characters. I will just focus on the braces, and after that I will have my braces and their positions. Okay, and then I will do what I did in my explanation on when I was explaining it using a pen pencil. And then when I say delete, I will mark them as deleted. And then what I will do in one pass, all the deleted braces will be ignored and I'll create a string. So that's what I have done here. So you can see once I have declared my two data structures, which is a list, which has a pair of char and int. Char is the brace and int is the position of that brace in the string, and a mark array. Okay. The mark array is of size n, so it tells which character I have to delete. So now it's plain and simple. So far so good, right? If it is an open brace, then I push it to my stack. If it is a closed brace, then I am not returning, I'm continuing. I go to the next character, right? That's what I'm doing. One more point to remember here is that my mark is all initialized to false in the beginning, which means I assume that everything has to be deleted. So when I continue here, which means that character is going to be deleted, right? Continue means I will move to the next element. So this means delete that character because it is already defaulted to false. If it is not matching, again, continue, which means, okay, it will remain false. But if it did not return here, then I go ahead and say that this brace will not be removed. This is marked true. We will not be deleting it. And we will also not be deleting its corresponding closing brace, right? Both of them are not going to be deleted. And I do a stack.pop. I pop both the matching parentheses. And at the end, all I'm doing is I'm just checking, if you can see, if mark is, so firstly, I see if it is a brace. So if it is an English character, then I'm not going to do anything. It becomes part of my result. And if it is not a brace, it becomes part of my result. If it is a brace, then I check whether it was marked true. So only if it was marked true, then I insert it in my string and I output that string. Okay. So that was a small implementation detail which I wanted to give you guys, that even if you know the approach, it is very important to keep implementing solutions, because a solution can look good on paper, but implementation can vary a little bit. So we had to introduce an array to mark all my deletes. And then in one pass, in order of n, I was able to create a new string. Okay, so this res.pushback is just pushing characters to my string. So all English characters are pushed here and all braces are pushed only if they are marked true. And then I return my answer and this will get accepted. Okay, so any questions before we move to the next problem? Can you explain the approach? Got confused on mark. Okay, so let's understand what mark is doing. Okay, and for that, I think I will again go back to my pen and pencil. Okay. Are you guys able to see my screen now? Can you see my screen? Can somebody confirm?
Yes. Yes.
Yes. Okay, awesome. So now let me explain what I meant. Okay. Yeah, admit first. Yeah. Okay. So what I was saying is that, let's say this example. Lead code and punch some. Okay. So this is my example. What I will say that firstly, if it is a English character, nothing matters, right? So we will break down this problem to this problem. And I'll note the positions. That position of this is 3, 4, 5. Okay, whatever the positions are, just note them. I will just mark something. Okay. So now this becomes your input. Now you start traversing this. Okay. And you have a stack. So you get the first brace, which is the opening brace. You insert this into your stack. Second brace is the opening brace. Again, you insert this in your stack. So now you are inserting a pair, which is character and int. That's what that vector was. Now, when you get a closing brace, then you look at top of your stack and just compare that what is the brace here. They are matching. I'm happy. So I pop this out. And I will also mark that these are not to be removed, both of them. Okay. We will not delete them. Okay. I'm marking if they are not to be deleted. Now comes the next input, which is again a closing brace. So again, top of my stack is a opening brace. So I'm again happy. So I pop this. And again, I mark that this index has not to be deleted and this index also has not to be deleted. Now I get my closing brace, which is and my stack is empty. So this is an error. So I say, I do not mark it as not to be deleted. So now when I will traverse this list, okay, then I have everything marked but this. So I will start with a string which is empty and I'll keep appending characters, append delete L because it's an English character, append E, append this because this is marked true, append everything until you reach the last character, which is not marked as true. So we will not append it to my string and my answer becomes everything blah, blah, blah without this last character. So ends with an, right? And with 2 opening and closing brace. And why I needed to do this? Because let's assume that you do not maintain a mark array. Then the error that you will get is, let's say that something like this is there, right? So now you want to delete any one of these, okay? So if this is your string and you need to remove one opening brace, then you will have to create a new string and do this deletion, right? That is, so if you start deleting each character when you figure that out, then it becomes difficult for you to solve this problem in a list. So let's say I have to delete these 2 characters. So first deletion, you will take order of n time. Why? Because if you remove this character, you have to shift all of them 1 space ahead, below, previous. So you do this and let's say you have to delete this again. So again, you will take order of n time because removal of this means removal of all characters which are ahead of this to 1 place back. So again, so rather than doing this, if you mark that these 2 characters are to be deleted or all the characters that are to be deleted in this huge string, then in one pass, you will just start with a string which is empty and keep appending those characters which are not marked to be deleted. And that's it. Like in one pass, in order of n, you would be able to delete all the strings that you have marked, rather than if you just go and delete as and when they come, it will take order of n time each time and times the number of elements that you are deleted. That will screw up your time complexity. So does that answer your question, Pooja? I think you asked that question. Does that help? Were you able to understand? Okay, cool. So let's go back to our original agenda. Okay. Back to the slide. Right. So now, balancing parenthesis 2 is done. Okay. Which is parenthesis 3. Then this is, you are given a parenthesis S. In one move, you can insert a parenthesis at any position of the string. For example, one example is given. You can insert an opening brace, okay, to be this, or a closing brace to be this. So you need to return minimum number of moves required to make S valid. So here you want to add braces to make it a valid parenthesis. Okay. But one more catch is there, that I don't want the output string. I just want how many braces you are adding. So in this case, I will just add one opening brace, okay, and this will fix my problem. In this case, I will have to add 3 closing brace and it will fix my problem, right? So this is the question, okay? The previous question was how many minimum number of deletions you have to do to make it balanced, and you have to output the string. In this case, there are 2 changes. Firstly, you need to figure out how many insertions you have to do to make the string of parentheses balanced. And here you just need to give me a number, not the string. You just need to give me how many. Okay, that's a plain and simple question. So now this turns out to be a very interesting problem, and we will actually solve this. Firstly, let's understand that. Firstly, let's read the question and try to understand that what is the question and how we can solve this. So again, a parenthesis is valid only if, so this is the validity condition which you can skip. And again, the question is same, that you are given this string, you can insert an opening parenthesis to be this. So this will be count as one move. And next time you will have to again insert one more to make this valid, right? So there are some input. In this case, you need to make 1 insertion. In this, you need to make 3 insertions. Any questions on the question first before moving ahead? Any questions? Everybody is able to understand the question? You need to tell me how many insertions are needed to make this string balanced parenthesis. I don't want what insertions. I don't want the output. I just want a number. How many number of braces you will have to insert? It doesn't matter if it is an opening brace or a closing brace. I just need a count. Okay. Clear? Okay. So now let's go back to the pen and pencil and understand how we can solve this problem. Okay. So now the question is that you have some question, right? You have a string. And now you need to find how many insertions you need to make this balanced. So clearly in this case, there is 1 insertion. But how we'll figure it out? Let's go back to our trivial stack method. So whenever you see a parenthesis, now so far you would have understood that go back to your stack implementation of the first problem, which was if a string with parenthesis is balanced or not. And let's see how will that solve this problem as well. So you have a stack and you have this input, right? So we'll start with a stack and let's see if we can improve it or what improvements we'll have to make. So we insert this. This is opening brace, we insert it, right? Next brace is again opening brace, again we will insert it. And next we get a closing brace. So when we get a closing brace, what will we do? Anyone? Are we going to insert the closing brace or are we going to pop something out of the stack? Anyone? What happens when you get the next closing brace? What do you do? There are 2 things that you do actually. Pop. Firstly, you check if pop can be done, if it is empty or not. And if it is not empty, then you pop. Okay. So we'll pop. Now what happens? Now, important thing to note. The stack is left with only 1 element. What does this say? Can anybody tell? So the question is minimum number of insertions to make this balanced. And you ran your valid parenthesis code and you are seeing that 1 element is left on the stack, which means it is not valid, which is expected. I need to figure out how many insertions I need to make to get it balanced. So what will be your answer here?
1.
You see that 1 opening brace is there in your stack. So how many insertions will you need? Anyone? Any takers? So you ran your valid parenthesis algorithm and you end up with a stack which has just 1 element. What does this say? That these elements in the stack, they have to be opening braces, right? Only opening braces are pushed. So if opening braces are left stray, that means they were not closed. So now go ahead and close them, right? So the number of braces which are left on the stack tell you, yeah, the size of the stack tells you that how many more insertions you'll have to do. But is that the only case that we are going to encounter? Let's see that if it will solve in all scenarios. Okay, let's pick another scenario. Stack representation is always an array with one side open because there is no fixed size. And of course, because you can only insert and remove from one end, right? That's how we represent it. Okay, here, what do we do here? The first element is a closing brace. So what does that mean? What does that mean? If you get the first element as a closing brace, then what does that mean with respect to the question? How many insertions I need to do to make it balanced? Whenever you get an error, like in the previous problem, whenever you get, what are error conditions? The stack is empty when a closing brace comes, which is this case. The stack has a brace which is not matching when a closing brace comes, which is impossible because there are only two types of strings here. So the second condition is not valid. So the only condition when a closing brace comes is that the stack is empty when a closing brace comes. That's an error condition. And the second error condition is that at the end of traversal, your stack has some opening braces. So for when your stack has some opening braces, we have already solved that. We will check the size of the stack and that many closing brace insertions have to be done. But what happens when you get a closing brace? So whenever an error comes, do a +1. Simple. It's very simple. So in the previous problem, you were deleting whenever an error came. Here, whenever an error comes, do a +1. So when this error comes, +1. When again this error comes, +1. Again this error comes, right? Because the stack is empty and a closing brace is there, +1. Now let me make the input a little bit skewed, right? Now the second is a closing brace, opening brace. So I insert it. Second is also a closing brace. I insert it. Third one is the closing brace, but now the stack is not empty, right? So stack is not empty, so I'm able to pop something out and I'm happy with it, right? Now the stack is, now the traversal is done and stack has one element. How many elements are there? Only one. So again, +1. So how many insertions I need to do? +4. And that's the answer. So every time you get an error in your valid parenthesis code, you will just do a +1 and you will get the answer. Any questions so far? Any questions? Any input? No questions. So now this, why I picked this problem, because this is a little bit more, it has a little bit more material than just this. Turns out that you can solve this problem even without using a stack by just doing +1 and -1. Let's see how. So if the only parenthesis is one type of parenthesis, then you can solve a valid parenthesis question and this type of question without using a stack. Let's see how. So you'll just have a counter, okay? So firstly solve the valid parenthesis with only small braces and then we'll come to this question. So let's say you have your trivial question of this and you want to see if this is valid or not. So what do? You just have a counter. And this counter will be +1 for every time you get a opening brace and a -1 every time you get a closing brace. So the first brace is what? Opening brace. So counter starts with 0. So now the counter is 1. Second is also opening brace, count is 2. Third brace is a closing brace, so count is 1. And the fourth brace is a closing brace, so count is 0. Let's take a imbalance scenario. So you start with this. Counter goes +1, counter goes 2, -1, reduce from 2, 1, reduce 0, and then -1. So seeing both the examples, what is the logic? When would you say that a string is balanced using the counter method? And when would you say a string is not balanced using the counter method? Counting, what we are counting? We are just counting +1 for opening brace and -1 for a closing brace. So if and in a balanced parenthesis, number of braces that are opened have to be closed. So at the end, counter has to be 0, right? If we get counter equal to 0, good. But there is a little more weight than just checking the counter at the end is 0 or not. And that is that anywhere in the middle, you should not have a negative counter. Okay. Example. This, you'll start with 0. First is a closing brace. You will do -1. Second is the opening brace. You will do 0. Is this a valid parenthesis? No. So there are only two conditions. Any point counter cannot be less than 0. And second is at the end counter has to be equal to 0. Only two conditions we need to check. Any point in the traversal, counter cannot be negative, because that means that we have closed more braces and there is no way now to add opening braces in the beginning, right? Because you're starting from the beginning. So any point you get a negative brace, that's a red flag. And at the end, if you don't get 0 count, that means they are not balanced, right? So absolutely right? So now we know that how we can solve for valid parenthesis using counter method without a stack if there is only one type of brace. Okay, that's the big if. That solution that we first did is still valid because we were solving it for multiple types of braces. Okay, this will only work if there are one type of braces. Okay, now let's go back to our original problem, which was minimum number of additions, minimum number of insertions that we have to do to make. And let's start with this. So far we were saying we will have a stack, and whenever you get error, like in this case, a closing brace comes, the stack is empty, you do a +1. Now opening brace comes, you put in your stack. At the end of traversal, there is one element in the stack, that's an error. So again +1, so +2. So answer is 2. But I'm asking it that can you do this without a stack using just counters? Can we do this? Can we get the answer +2 without using the stack? Let's see. You start with a counter, which is set to 0. And again, the same funda is there. If a closing brace comes, then counter will go -1. If opening brace comes, then counter takes into +1. Now, first brace is what? Closing brace. So counter goes -1. At this point, you will have a result. You will have an integer result, which will store the result. So whenever you get an error, this guy goes ++. That's what we are doing in the stack implementation, right? Whenever error comes, this guy will go ++. So यहाँ पे 0 से 1 हो जाएगा. And now, after this, you go 0, right? So -1, and then counter becomes +1. Here, you need to play a little bit more smart. So whenever you get a negative, whenever your counter goes negative, you reset that to 0, because that everything before that was invalid, right? So just reset back to 0, and then you get 1, and counter is 1, which means counter is not 0 at the end of traversal because of one element. So again, res will go ++. Let's see if this works at other examples as well. So remember, firstly, I'll write the algorithm. The algorithm is initialize a counter equal to 0, and initialize solution equal to 0. Counter goes counter ++ every time you get a opening brace, right? And counter goes counter -- every time you get a closing brace. But if counter becomes, at any time counter becomes -1, then you reset the counter. And whenever you reset, you know that is the error condition. So जब भी error आ रहा है तो solution ++. And at the end of this, right? 1 second. At the end of this, basically, I don't have a space, so I will go to the next slide. At the end, if whatever is the value of your counter, at the end, your solution plus equal to whatever your counter is there right now. मतलब जितने भी braces are there left, opening braces are left on the stack, you will be adding that to your solution. So this is just a simple solution that whenever an error comes, error कब आएगा? जब counter goes negative, reset the counter, solution ++. Every time an error comes, you increment your solution. And at the end, if there are stray opening braces, then just add it to the solution. Okay. And now let's see if this works on a bigger example. Okay, let's see if this works. So our counter starts with -1. Solution So this is your counter starts with 0, solution starts with 0. Counter becomes -1 and solution becomes 1. Whenever counter becomes -1, we make it 0. Now, next is opening brace. So counter becomes 1, solution remains 1, nothing happened. Closing brace, counter is not negative still, we are happy. Solution is still 1, no new insertions. For this, we needed insertions, no new insertion. Now here, counter goes +1 because the opening brace come. Solution is still 1 because so far so good. Now you get a closing brace, counter becomes 0, solution still remains 1. Now you get an opening brace again, counter becomes 1, solution still is 1, so far so good. Another opening brace come, counter becomes 2, solution is still 1, so far so good. Now you get a closing brace, counter goes to 1, solution is still 1, but you reach the end of traversal. What is your counter? Your counter is left. So what do? Solution plus equal to counter. Solution equal to 1 plus 1, 2. So I need insertion for this bracket and this bracket, which is right. So if I make insertion here, and for this closing brace, I add another closing brace, then we will be balanced, right? Remember, counter was positive, which means there were extra opening braces. So I need one more closing brace. So 2 is the answer here. This is balanced, this is balanced, this is balanced, and this string is balanced. Hence, this parenthesis is balanced. So turns out that you can solve this without using a stack, using a two counters, one counter and one solution. Okay. So now I will stop this share and we'll go to the lead code implementation of this problem, and we will see that how we can solve this problem. Minimum. Yes. This is this is the question. Minimum addition to make this valid. So are you guys able to see my screen? Lead code screen, everyone? Can I get a yes? Is my screen visible, guys? Can somebody confirm? There is some lag generally. Can somebody tell me if my screen is visible?
It's visible.
It's visible. Okay. So minimum additions to make it valid. Like I said, we will start with a res and a solution. Both will be 0. Whenever you get an opening brace, then this res is counter. Okay. And solution is solution. So this goes plus plus whenever you get opening brace, goes minus minus whenever you get a closing brace. But whenever this reaches -1, which means that, what does this mean? -1 aa gaya matlab ki now you have to reset the counter. Counter is reset, but this also means that an error has occurred. So jab bhi error hota hai, we need to make an insertion. So solution plus plus. And at the end, whatever is there in your counter has to be added back to the solution. And we return the solution. And this simple code, without using a stack, gets accepted in ahead of 100% of C++ solution, clearly, because we are not using any stack to solve this. Any questions? Any questions before we move further? Is this clear? Any doubts? Any questions? This is the last question of balancing parenthesis part. Now we'll move to other segments of stacks. Any questions as of now? Okay, cool. So now we will move to the next part. Okay, so now time for a quiz. So I will launch a quiz. And let's see. Okay, so the quiz is that how many strings of length 5 comprising only of small brace open and small brace close can exist which are balanced? And this is a single choice question. How many strings only with, so basically this is a question of how many combinations of open and close brace of length 5 can exist which are balanced? Is everyone able to see the poll? Quiz? Is everybody able to see the quiz? So the question is that how many strings of length 5 comprising of only open and close braces can exist which are balanced? Anybody wants to take a go? 10, 11, 0. 3 people are saying 0, 2 people are saying 10. Anybody wants to unmute and speak? Why they think answer is 10, 11 or 0? You can draw on your pen and pencil and see how many possibilities are there. It's a simple question. Anybody wants to explain their answer? So I see a lot of people, 56% of you have said that answer is 0. 2 of you have said that it is 10 and 2 of you have said that it is 11. Okay. So for those who are saying 10, can somebody tell why it is 10? Yeah, so we have one answer. That for the string to be balanced, it has to have equal number of opening and closing braces. If the opening and closing braces are equal, then the string size has to be even.
So for
if
5,
the string is of length 5, which is an odd number, then it is impossible to have equal number of opening and closing braces, right? If the string is only comprising of opening and closing braces, then it will be impossible to have an odd number string which can be balanced. Yeah, somebody was saying something.
yeah, so for I was giving the answer for I mean justification for 10, which was my answer, that we can have a 10 strings, means each 10 5s are 50, so it will become an even number, so there will be a possibility that we have a balanced string.
Oh yeah, so no, so question is that how many strings of length 5, like each string is of length 5. So how many such strings can exist which are balanced? And the answer is 0, because no string of length 5 can be balanced because it has odd number of braces. So odd number of braces can never be balanced. So whether you have 10 of those or 50 of those, all of those will not be balanced. So the number of strings which are of length 5 are infinite. Number of strings of length 5 with only opening and closing brace are 2 to the power 5, which is 32, but none of them will be balanced, right? So does that answer your question?
Yes, so I misunderstood that. I thought that we need to combine all the
we
strings
don't need to combine them.
Yeah.
Okay, cool. So end this poll. Okay, so now let's move to the second part. Okay, so now Zara, are you there on call?
Yeah.
Yeah,
Am I audible?
just yeah, I'll stop my screen share. Yeah, you can. So Zara will give you some update about yeah, Zara, you can go ahead.
Hey guys, are you here from Expertify? Hope you are doing well. Yeah, wanted to let you all know that at Expertify, we have data structures and algorithms and system design in our online live sessions as well as self-paced courses.
Your voice,
Guys,
you're cutting off, Zara. We are not able to hear you well.
I think there is some network issue there.
Okay, cool then. I'll take it. I'll take it. No issues. Yeah. Yeah. So basically, I'm an instructor in Expertify, which is interview preparation company. There are live training and self-paced courses, which you can purchase from the website, and their website is www.expertify.com. If you want to contact any of Expertify support staff, then this is their contact number. So just a small pitch on the marketing. Thank you, Zara. I'll take it forward from here. Okay, so any questions? Yeah. Any questions so far? Now we are done with the parenthesis based questions on stacks. Turns out there are not many. Like these will be sufficient for you to encounter any stack based parenthesis problem. Any questions before we move to the next type of problem, which is very common in stacks? Before we proceed ahead, any questions? Okay. No questions? Okay. So now let's come to another segment of problem, which is done using stack, which is next greater element. Okay. So next greater element is given an array. So next greater element is, let me explain this with this diagram. Yeah. So let's say you have an input 1, 2, 3, 4, 5. So for 1, the next element to 1, matlab 1 ahead of 1, which element is there which is greater than 1? So that is next greater element for 1. Okay. So for 1, the next greater element is 2. Sorry. Is 2, right? Because ahead of 1, which number is greater than 1? 2. Ahead of 2, which number is greater than 2? 3. Ahead of 3, which number is greater than 3? 4. Ahead of 4, which number is greater than 4? 5. Ahead of 5, which number is greater than 5? There is no number ahead of 5, so we say minus 1. So this is the next greater element array. This is which we call as NGE. Okay. This is a very famous set of problems are based using this approach. So we'll come why this is important, but firstly, let's understand the concept of next greater element. So any element in an array, you need to find the next element which is greater than that number, and that number becomes the next greater element. So for 1, 3 won't be next greater element because 2 is there, which is ahead of 1 and is greater than 1. So the first number that you encounter, which is greater than 1, after 1 is the next greater element. Any questions on this? Is this clear? Why next greater element is this? For 1, it is 2, for 2, it is 3, for 3, it is 4, for 4, it is 5, and for 5, it is minus 1. Similarly, in this input, 3, 2, 4, 7, 8, 2, 1. What will be the next greater element of 3? So ahead of 3, I'll start moving and I'll see which number is greater than 3. I get 4. So 4 becomes the next greater element of 3. Ahead of 2, which element is there greater than 2? 4. So I write 4. Ahead of 4, which number is greater than 4? 7. Ahead of 7, which number is greater than 7? 8. Ahead of 8, which number is greater than 8? None of them. So minus 1. Ahead of 2, which number is greater than 2? Nothing. Minus 1. Ahead of 1, which number is greater than 1? There is no number ahead of 1. So again, minus 1. So the last number will always have minus 1 because there is no number ahead of it, right? So no question of greater or smaller. So is this much clear? Next greater element. What do we mean by next greater element? Any questions on this? Okay. So now let's see how we can solve this. Okay. So now again, I will go back to my pen and pencil. Sort of, yeah. Let me know if you guys are able to see my screen.
Yes.
Thank you. Okay, so now let's start with the problem, which is that given an array. So firstly, I'll give an array and you need to tell me what is the next greater element array for this. So can everybody write in chat what is the next greater element array for this? Basically for 5, what is the answer? 4, 3, 2, 1, and this becomes the array. So what's the answer for this?
All minus ones.
Right, all minus 1. So in a descending array, this will always be all minus 1s. Now let's come to some general. Okay, so for this, what will be the next greater element array? Can people write this in chat before I write it? For this array, what is the next greater element array?
8, 9, then
Okay.
minus
So for 5, it is 8. For 8, it will be 9. For 9,
minus
it will be minus 1. For 3, it will be
minus 1.
For 9, it's not minus 1, right? For 9, you have 12.
Okay.
So for 3, you will have 12 again. For 2,
Okay.
12. For 1, 12. And for 12,
Minus 1.
minus 1. Any questions so far? So,
No.
yeah, okay. I hope, Harsh, this is Clear, I think 2 of you. Why -1? 12 is there, right? Okay, I hope it is clear. Okay, cool. So now that we all know that what is next greater element array, now let's try to figure that out, how you will solve this. Can anybody tell in layman approach how you will solve this? Like brute force kya hai? Matlab, how you are figuring it out. So ahead of 5 you are looking, so matlab we can have a for loop for I equal to 0, I less than n, I plus plus. For each I, you will have a inner loop for j equal to I plus 1, j less than n, j plus plus, right? And whenever you get array j greater than array I, that becomes the next greater element for that, right? For this 5, you will start a loop from 8, and at 8 itself, you see that 8 is greater than 5, so 8 is the answer. For this 8, you will start a loop from 9, and at this 9 itself, you found it. Good. For this 9, you will start a loop from 3. 3 is smaller, 2 is smaller, 1 is smaller, 12 is greater. So 12 is the answer. For this 3, you will start an inner loop from 2. 2 is smaller, 1 is smaller, 12 is greater. 12 is the answer. Similarly for 12, and similarly for 12, you have no element, so it is -1. So using a O(n) square approach, right? For each element, iterate at worst case order of n time and figure the answer out. And there are n elements, so times n. Order of n square approach, you will be able to find the next greater element array. Any questions on this? Is this approach clear? This is the approach using which you guys are writing the answer. Basically, that's what you're doing in your mind. In order of n square time, your mind is able to figure out what is the next greater element of the array. Any questions on this? Sir, it is the time. No. This is not the time complexity of the problem. This is the time complexity of this approach. The solution for this problem is a quite optimized solution. We'll come to that, but this solution, the brute force solution, is order of n square. We'll try to see how we can improve, if and how we can improve it. Okay, so now let's come to the improvement part. And no surprises, we will improve this using which data structure? Stacks, right? So let's have an array. Okay, so let's have this array and let's have a stack. Okay, so now the approach is that whenever you get a number, you push it to stack if the stack is empty. Okay, if the stack is empty, push that number to stack. Then you move to the second number. Now for the second number, whenever you want, now you want to push 3 in the stack, but before pushing, see what's the stack top. What is the stack top right now? What is the stack top right now? Anyone? I hope this is clear that the stack top is 1, right? So yeah, good. So stack top is 1. So whenever you find you are going to insert, you want to insert a number to the stack, but before inserting, you check what the stack top, and you see that the stack top is less than that number, then clearly 3 can become, so we will pop, forget about, just listen to the approach first. So we'll pop until either the stack is empty or the stack top is greater than the number you want to insert. So what's the number you want to insert? 3. So, and what's the number at the top of stack? 1. So I will keep popping until a number comes which is greater than 3 or the stack becomes empty. So I will pop 1, the stack becomes empty. But for 1, I know that 3 is greater than that. I'll write the answer 3. Okay. We'll come to the algorithm first. Let's hear out the approach first. Then we will see how it works and why it works. Okay, so for 1, we got the answer 3, simply because 3 popped 1 out. And after you have popped 1 out, now that the stack is empty, you will actually go ahead and push 3. So now 3 is in. Now the next number is 2. So you want to push 2. The top of your stack is now? The top of your stack is now 3. Is 2 greater than 3? No. So we were popping only if the number in the stack, the number at the top of stack is smaller than the number you are inserting. So 2 is the number that I want to insert, and 3 is the top of the stack. It's not smaller than the number that I'm inserting. So now I will go ahead and insert 2. I'll not pop anything out. Okay. Now 8 comes. So 8 comes. What is the top of his stack now? 2. Is 2 smaller than 8? Yes. So for 2, we will say, we will pop 2 out and we will say, because of 8 you were popped and 8 is your next greater element. Now what's the top of my stack? After popping 2, what's the top of my stack? 3. 3 is also smaller than 8. So like I said, we'll keep popping until we reach stack top, which is greater than 8, or the stack goes empty. So we'll again pop 3. And 3 was popped out because of whom? 8. And now that the stack is empty, now we will go ahead and insert 8. Okay. Now we move to the next number 3. So we want to insert 3 and we see that the top of a stack is 8, which is greater than 3. I'm happy. Now the next number is 4. What will happen at 4? Anyone? I want to insert 4 and this is my stack. What do I do? We pop, we push. What do we do? Anyone? With the same funda. We want to insert 4. Top of my stack is 3. So what do I do? Because top of my stack is smaller than the number I want to insert, we will pop 3. Absolutely right. We'll pop 3. And answer for 3 becomes, kiske chalte 3 pop hua hai? 4. Now, what's the top of my stack? 8. What's the number I want to insert? 4. Is 8 smaller than 4? No. So now, no more popping. And 4 goes inside. Now the next number is 6. I want to insert 6. But I see that my stack top is 4, which is smaller than 6. So I say, okay, get out. And answer for this is 6. And the next stack top is 8, which is not smaller than 6. So now we insert 6. Now, every element inside this stack has no next greater element. We'll talk about why we are doing this, but we'll pop them and we'll say -1 and -1. And now let's see if this is the valid answer for this array. ठीक है, ये तो निकालना, everybody knows how to find next greater element for this array, and let's see if our answer matches the approach that we were using. So for 1, 3, for 3 it will be 8, for 2 it will be 8, for 8 nothing, -1, for 3 4, for 4 6, for 6 -1. Is the answer matching? 3 8 8 -1 4 6 -1. Yes, the answer matches. Yeah.
Can you repeat how did the 3 in the stack was removed?
Okay. Yes, let's go back. Okay, what we will do? We will go and do this for the same problem again. 1 3 2 8 3 4 6 1 3 2 8 3 4 6. Okay. Okay, so hopefully other people will also have the same question. Gets answered. Again, I'm doing this. Now I will write the algorithm and then I will do, so that you guys know the algorithm first. So the algorithm is, if stack is empty, then push whatever is there. And if the stack is not empty, then while stack is not empty and stack top is smaller than the number, let's call that number x. Okay, x is a variable. So if that is smaller than that number, then you will stack.pop. And once either the stack becomes empty or you get a stack top which is greater, then you will do stack.push x. Now that this algorithm is written, using this algorithm, we will be running through this again. Okay, so this is our stack. What's the first number in the array? 1. Is my stack empty? So my stack is empty, so what will I do? My stack is empty. So look at the algorithm and just write the answer in chat or somewhere. Better, you'll get a better understanding. So I'm looking at 1, my stack is empty. So if my stack is empty, I will simply push, right? So 1, goes in. Now, next number is 3. And before inserting 3, stack is not empty, first thing. So first condition is not. I'll check the second condition. So now I see that the stack is not empty. And what's the stack top? Is the stack top less than 3? Is the stack top right now less than 3? Yes, no, anyone? Stack top kya hai? 1 hai. And 3. Is the stack top less than 3? Yes.
Yes.
Yes. So what will I do?
We will replace 3. So
Pop.
1, 3.
Yes. No, we will not replace. We will pop
So
1.
we'll pop it.
Yeah, and we will write that the answer for 3 is the reason why 1 was popped because 3 was going to be inserted. So we'll write 3 and then we will insert push X is also there. So we will insert 3. Now what happens? Next number is 2. So we want to insert 2. So what will happen now? Is the stack empty? No. So is the stack top less than 2 when I'm inserting 2? Stack top is 3. Number I'm inserting is 2. So is the stack? No. So what will happen? Stack dot push simply. Now, next number is 8. So now the stack top is 2. Is 2 less than 8? Yes.
Yes, sir.
Pop. And now this is inside a while loop, right? So we'll keep popping until the stack is empty or we reach a stack top is greater than 8. And at this point, we'll push it. And the reason because 3 and 2 were popped was 8. So 8 and 8 was the answer. Now 8 is there. Now we want to insert 3. So 3, stack is not empty. So we'll just insert 3. Stack is not empty and the stack top is greater than 3. So we'll insert 3. Now 4. Now we want to insert 4, but we see that the stack top is 3. So we'll pop 3 first. And we'll write why 3 was popped. 3 was popped because of 4. And 8 is not smaller than 4. So now we will go and happily insert 4. Now the next element is 6. So 6, the stack top is 4. 4 is smaller than 6. So we'll pop 4 out saying that, okay, you have been popped because of 6. And we'll insert 6. And then we will pop 6 and 8 out saying that your answers are -1 and -1. So in this process, we were able to figure out that 3, 8, 8, -1, 4, 6, -1 is your next greater element array. Okay. Now, does that answer your question? Now, is it clear about it? Okay. Now let's come.
What is the use of next greater element?
Sorry, what is the
Use of this algorithm?
Yeah, we will come to that. We'll come to that. Firstly, we want to know what it is. There are lot of uses, but I'll not go there. There is the problem that we will solve. Why we are studying this. Okay, so firstly, next greater element, why this algorithm works. So this algorithm that I have written here, why does it work? It works. I hope a lot of you would have guessed it why it works. It simply works that we are storing every element on a stack, and before inserting an element, we figure out all the elements which are on top of a stack which are smaller than it. So then and there we get the next greater element of those elements, right? And at the end, whatever elements are left, they are all they don't have any next greater element at the end. So all of them become -1. So that's why it works. It's very simple why it works. And in this way, one more important thing to note that we were able to reduce the time complexity. So this approach, time complexity kya hai? For this approach, you can see for each element you are iterating and doing 2 steps, 1 and 2. 2 has a while loop, but what can go inside that while loop, right? If you carefully observe, then the time complexity of this is also order of n. You are doing this for every element, but you will pop at max n elements throughout the algorithm, right? You are not inserting the same element again and again and popping. So is while loop ke andar popping can have at max throughout the execution of this algorithm can have n times. So this becomes order of n algorithm. So this is being solved in order of n time, and space is also order of n because you are using a stack. Okay, so you reduce the problem solution from order of n square brute force to order of n time using a stack. So far, so good. Any questions? Anybody is having any doubts, any questions before moving ahead? We have one question why we are studying this, which I'll answer. But any questions so far? No question. So I have a great question for you guys. And let's see how many people are able to answer. The really smart question. The question is that you know how to solve next greater element, right? Now you know how to solve next greater element. Can you solve for previous greater element? Let me give you an array. 1, 3, 3, 6, 5, 4. So you know what is next greater element for every element. What's the next greater element? So now this is the array, and I'm asking you populate. Firstly, don't think about the approach. Tell me the answer of previous greater element for this array. Tell me what's the answer. Is there any data structure other than stack? No, Pooja. This can only be used using stack. No other data structure that can solve this in order of n time. And you can't get rid of the stack as well. Okay, so now let's come to this question. Now that you know what is next greater element array, similarly, I'm not asking for the approach. I'm asking you what will be the previous greater element array. Can anybody write? Previous greater, next greater क्या होगा इसके लिए? पहले वो लिख दो. What will be next greater element for this array? Can someone write in chat or someone tell next greater element for this array? -1. So not 1 for the entire array. For this array, next greater element will be for 1 it is 3, for 3 it is 8, for 2 it is 8, for 8 it is -1, for 6 it is -1, for 5 it is -1, for 4 it is -1. Okay, so this is the next greater element array. Similarly, what will be the previous greater element array? -1, -1. Let's see. So for 1, what is previous element to 1 greater than 1? Nothing. For 3, -1. Yeah, greater than 3. Okay, previous greater element. So 3 ke piche there is no element which is greater than 3. For 2, there is an element behind 2 which is greater than 3, which is 3. Greater than 2, which is 3. For 8, there are no element behind 3 which is greater than 8. Sorry, for 8, there is no element before 8 which is greater than 8. For 6, there is no element. Is there any element before 6 which is greater than 6? Yes, 8. Is there any element before 5 which is greater than 5? Yes, 6. For 4, 5. So for first element, it will always be -1. Just like next greater element for the last element is always -1. But this is the answer. And that was rightly given by Shweta. Yeah. Okay, Harsh also. Yeah, good. Good that you guys were able to figure this out. So previous greater element is also done using like this. Now, for all you guys, how will we compute previous greater element? Random array. Previous greater element we want to compute. Can we use stack again? Answer. Can anybody think there is one small modification that you can do in your next greater element solution and you will get the answer for previous greater element? Same algorithm by traversing the array in reverse order. Awesome. Absolutely right. Same algorithm as next greater element, traverse in reverse. Let's see if that works. Stack is empty, first element is 5, I'll insert. Next element is 1. When I'm inserting 1, then is the stack top smaller than 1? No, I will insert 1. Now 2. Now comes 2, right? So now for 2, I want to insert 2 in my stack. Is the current element, is the stack top smaller than 2? I want to insert 2 and I see my stack top.
Yes.
My stack top, yes. So I'll pop and what I will say. Answer of our 1 is 2. Is my stack top now, after popping 1, is this still smaller than 2? No. So now I will insert 2. Now the next element is 3. I want to insert 3. Is the stack top less than 3?
Yes.
I will pop. And answer for this 2 becomes 3. And now again, same question. Is my stack top still less than 3? No. So now I will push 3. And finally, we have 1. So we want to insert 1. And we see that the stack top is greater than 1. So we simply insert. And now for all of this, we will pop. We will say for 1, it is -1. For 3, it is -1. Okay. Is this the correct previous greater element? For 1, correct. 3, correct. 2 ka 3. 1 ka 2. For 5, -1. Works. same algorithm, from n minus 1 to 0, iterate from n minus 1 to 0, gives you the previous greater element. Okay? Any questions? Any doubt? Exact same algorithm. If you run from left to right, you get next greater element. And of course, if you run it from right to left, you get previous greater element. Simple. Now coming to the question that why we are doing this, right? Okay, so now let's come to the why part. Let me ask one question. Okay, and I will frame one question, which is a very famous interview problem. You are given a histogram. This is 3, 5, 6. Okay, this is 3, this is 5, 6, and let's have a 4. Let's have a 1. Okay. So now question is that you need to find the largest rectangle that I can fit in this histogram. And hint is that it can be solved using what we have discussed. Can anybody think how? This is a histogram. Everybody knows what a histogram is, right? Histogram is something like this, right? These are all your bars. And you need to find the largest rectangle. So I will tell one of the rectangles can be this. It may not be the largest, or this is one of the possible rectangles. Another possible rectangle can be this, right? So similarly, amongst all the possible rectangles, even this itself is in a rectangle, right? So which rectangle has the largest area? That's the question. And how you will solve this in as best time complexity as possible. Okay, so I will tell you. This is one of the hardest interview problem, and it is solved using this question, this simple approach, what we have discussed, next greater element and previous greater element, and you will see how. So before doing that, can this rectangle, this small rectangle, be the answer ever? If a rectangle is not bounded by length of one of the histogram, can it ever be the correct answer? Matlab, this may be a contender, but this definitely will not be a largest rectangle because there is a possibility of creating another rectangle of height 4, right? So possible answers for largest rectangle in a histogram, the length of that has to be either 3, 5, 6, 4, 1, and 2. I'm talking about the length of the rectangle. It should either start with 3, 5, 6, 4, 1, or 2. Matlab 1 can also be. This may be the largest rectangle. I don't know. This may be. But I am sure that 0.5 length, if I create a rectangle of a subset of this, will never be a largest rectangle. So is this part clear? That a largest rectangle will be a rectangle with length 3. We don't know about the width, but the length has to be either one of these. Yes or no? Clear? Okay, some people are suggesting some answers, which seems correct. But yeah, firstly answer my question. Like, this is clear, right? That the length has to either be one of these integers, right? So this histogram has these elements. And the length has to be either of these 3, right? It is impossible to have a largest rectangle whose length is different than either of these numbers, right? You will not have. Okay, now let's come to the second property. So now, can I say that I will pick one of these histograms and I will see how much left I can go. So from 4, I will start creating a line towards the left, and I will see how much left I can go. So here I can go, here I can go, but here I see I can't go. So I will stop here. So I will stop at this index. And similarly for right, I'll see how much right I can go. I'll start from here and I'll see I have to stop here. So what is the width of this? There are 3 elements, and the height of this is 4. So 4 times 3, so this becomes 12. So a rectangle of length of 4 is 12. So for 4, I get answer is 12. Similarly, I repeat for 6. So if a rectangle were to be created of height 6, then how much left I can go? Just this element. How much right I can go? Just this element. So 6 times 1. So for 6, the largest rectangle possible of height 6 is just 6. For 5, how much left I can go? I can go left to one index. How much? Sorry, I can go right to one index. How much left I can go? Nothing. So I can go from this index to the next index, which is 2. So for 5, I can get 10. Of height 5, a rectangle of height 5 is 10. For 3, how much right I can go? Left, obviously I can't go any left, but how much right I can go? I can go up till 1, 2, 3, 4 places. So 3 times 4 is again 12, right? And similarly for 1 and for 2. But the question that you are asking, what question you are asking? At each element, you want what is the previous smaller element. 6 ka previous smaller element is 5. So here only the line will be terminated. The line is starting at 6 length will have to be stopped. Let's draw a new histogram and now see it in that lens of previous greater element. Okay. So let's say this is a histogram. And you are here. Okay. So you want to see how much will this span. So how much left I can go. Right. So turns out I can go left until the previous smaller element. So previous smaller element, let's name them 3, 4, 5, 6, 7. So previous smaller element to 4 is 3. So at index of 3, we will have to break this because this line can't go more here. Because this will not be a rectangle enclosed inside the histogram, right? Now, how much right I can go? This will be the next smaller element. So 6 is not next to 7 is not. Next smaller to 4 does not exist. So up till the last index I can go. So I can go up till the index of 3 and up till the index of the last index I can go, which means this is the, and if we know that this index is 1 and this index is, let's name the indexes. So we know that this rectangle is spanned from index number 1 till index number 4, right? So then we know that the breadth of this is 1, 2, 3, 4 times 4, which is area becomes 16. Similarly, so what my algorithm is going to be, for each element I want to find previous smaller element and next smaller element. And once we get the previous smaller element and next smaller element, then for each element, I just need to look at the index of these. So we have to store the index of the previous smaller element and the next smaller element. So for example, let's take this array. Previous smaller element we know, but now we will also, so previous smaller element, let's write that first. For 5, it is 3. For 4, it is 3. Right, for 6, previous smaller is 4. For 7, previous smaller is 6. Okay. But now we will not just write the number, we will also write the index. Okay. In fact, we are only interested in the index. So for 5, answer is 3. But we will write the index of 3, which is 0. For 4, again 3, index of 3 is 0. For 6, index of 4, which is 2. And for 7, index of 6, which is 3. Okay, so this is your previous smaller element. Similarly, you will create indexes of the next smaller element. Okay, so firstly, write the next smaller element for this array. The next smaller for 3. Similar, we did it for greater, you have to do it for smaller. So is there any element ahead of 3 which is smaller than 3? No. Is there any element ahead of 5 which is smaller than 5? Yes, 4. Similarly, ask the same question for 4. Smaller than 4, nothing. Smaller than 6, nothing. Smaller than 7. Again, nothing. So the answer becomes -1. For 5, next is 0, 1, 2. Right? And for all of these, there are no smaller elements ahead of them. Right? -1, -1, -1. Okay, and now using these numbers for each index, you know that the previous smaller element to 3 is not existent, and the next smaller element is also not existent. So here we need to be a little bit smart. So next smaller element, how will I? So basically from 3, if we look at the next smaller element, I can span all the numbers. So instead of -1, which was marking it is not existent, next smaller element will give an index n. Okay, it starts from 0, goes till n-1. And if the next smaller element is not existent, I will give an index n so that it is easier for me to calculate the breadth. With -1, I'm not getting a good information. I know it does not exist, but it also doesn't tell me that all the elements are spanned. So for next smaller element, we will start writing the n, which is 1, 2, 3, 4, 5. Start writing 5. Okay. So now all I need to do is for each element for 3, I know my rectangle can span from -1 to 5, right? Number before this till 5. So what does that mean? So a rectangle can start from 3 and it can span 1, 2, 3, 4, 5 rectangles. So what I will do, next smaller element minus previous smaller element -1. This is my breadth times the number. So 3 times 5 minus -1, 3 times -1, which means 3 minus 1 times 3, which is, these both go away, 50. So from 3, I can create a rectangle of size 15. Similarly, from 5, I will look at the previous smaller element 2, next smaller element, previous is 0, next is 2, 2 minus 0 minus 1, which is 1. So from 5, the rectangle will be 5. For 4, previous smaller is 0, next smaller is 5. So 5 minus 0 minus 1, 4, 4 times 4, 16. And for 6, 5 minus 2 minus 1, which is 2, we will have 12. And for 7, we will have 5 minus 3 minus 1, which is 1, 7. And we'll take the max of this, which in this case is, I think, 16. Right? So this rectangle is the largest rectangle that we can fit. So the approach is that compute next smaller element, compute previous smaller element, and then apply this formula that number I times previous smaller element, ith position, next smaller minus previous smaller, right? Larger index minus the smaller index, minus 1. This will give you the breadth, and you have to take max of it from I equal to 0 to n. So now boils down to the problem in how much time you can compute the next smaller element array. We have seen we can compute this in order of n time. This you can compute in order of n time. Once we will do this once stored in this array, and now we are just accessing the elements. Okay, so this whole thing is being computed in order of 1 time for each element. So overall time complexity becomes order of n. So firstly, you compute next smaller element order of n time, compute previous smaller element order of n time, and then take max of this expression through 0 to n minus 1, which is again order of n. So you solve the problem of largest rectangle in a histogram in order of n time. Okay, so this is the solution for this. This is the reason why we are studying this, and quickly I will go and show you that how this is coded. Okay, just give me a minute. Largest rectangle. This is the question which we are discussing. This is the same question. No need to see this and look at the answer. So just look at this code and you will see that how simple is the code, that I'm just computing the next smaller element. I'm computing the previous smaller element array, and then I'm iterating and I'm doing what I said, height times next smaller element minus previous smaller element index minus 1. So I'm computing this and solution and taking max of this solution, and I'm getting the answer. And I have a method to compute the next smaller element and previous smaller element. you can see they are very similar to what you did. For greater element, you were doing, if the number is, if the stack top is smaller than the number you are inserting was for greater. So for a smaller, you will do the ulta, which is if the stack top is greater than the number you are trying to insert, then you will keep popping. And by this small variation, you get the previous smaller and next smaller. And if you submit this, then in order of n time, you are able to find the largest rectangle in a histogram, okay, which is in itself a brute force solution is very bad. So you can see that we can, if we pre-compute the next smaller element and previous smaller element using stacks, okay, I'm using a stack to compute all of this, then I can simply apply this simple mathematical formula, length times breadth, and I will get the solution. So any questions so far? Are you guys able to follow this approach? This is considered to be a hard problem. So if you go in lead code, this is tagged as hard. So far we were doing easy and medium problems. Now this is the first hard problem that we have solved. So it's okay if you have some clarifying questions, happy to answer them before moving forward. Any questions? So the solution was that just like you computed the next greater element, we figured out a way to compute the next smaller element by just changing the inequality. Now that we know how to compute next smaller element, I will just do the iteration opposite. And I will get previous smaller element. And I populate this array. We populate this array, previous smaller element and next smaller element. Okay. And once we have populated this, we just apply this formula and we will get the solution. Okay. Any questions? We will find, okay, I see a lot of people. What are some good corner test cases for this? Corner test cases basically should be the correctness of your next smaller element and previous smaller element. If they are correct, the corner case was, like I said, like make sure when next smaller element does not exist, you are not storing -1. Rather, you are storing end of the array, index at the end of the array, which is n. So that you get the span, right? Rather than saying it is not existent, you say it is not, like, so that you can get the histogram, right? You can get the rectangle. So that's a corner case, that if it is not existing, you are writing for next smaller element, you are writing n here. And for previous smaller element, you are writing -1. Okay. This was the catch. This was the corner case. Apart from this, there is no corner case. You can see code is very simple, very clean. Just 2 methods and we have the solution. Code for PSE and NSE are very similar. Can we do something to abstract the common part? Make a function. Yes. So basically, you can abstract this part out, the for loop out, right? The function will be same. So you can have next or previous smaller element one method, and iteration part can be abstracted out and can be overloaded for 2 different types of scenarios based on either you can pass this as function parameter or you can overload this as part of, you can make this as an interface method, abstract method, and you can use virtual functions to implement them for previous and next. Up to you. But yes, if you just abstract this for loop out, all the code is same, right? I'm just traversing in one direction in one case and another direction in another case, right? Okay. Any questions? So I see somebody else has joined from, okay. Okay. Yeah, my polling session has become inactive. Okay, cool. So if somebody from Expertify has joined using co-host, Anil, I think. I think some staff from Expertify. Can you just drop my polling session has become inactive? I had some quizzes, which I don't know why has been inactive. Turns out 2 hosts can't exist. Okay, cool. Thank you. So, okay, permanently blocked. No issues, no issues. Okay, let's move back to my slide. Okay, so this was, I'm seeing that it's already going to be 12. So I'll stop here. I had some more items in my agenda, which I will just say. So this was the algorithm that we have already discussed for next greater element, right? We have already done this. Next was previous greater element, which we have done. right? Which you guys computed. And next smaller element, we now know how to do it. We just change the inequality. And this was the problem that we discussed, largest rectangle in histogram. This is the reason why we are studying Qs. These are the problems. And there is quiz 3, which is, I know what are the quizzes. The quiz is that what is the time complexity of next smaller element? Can everybody write on chat? What is the time complexity of next smaller element? To populate next smaller element, what will be the time complexity? Or next greater element, previous greater? What is the time complexity? Simple question. Order of n. Great. That was the question. Okay, so now let's move to the next topic. So next topic was trapping rainwater, which I can cover. I don't know. We don't have much time, but I can extend this to 5 minutes. But this will take some explaining. So I will skip that. Maybe in the next week we will cover this. So I have 3-4 more problems, which is trapping rainwater. Then this is another classic question on using stacks on strings. So stacks on strings, similar to parenthesis question, right? And after this, we'll come to what our favorite part was. So our favorite part was this parenthesis score problem. Again, back to parenthesis problem. So this is again a hard question, which I will not cover. It will take a lot of time easily. So I'll stop here and I will take any questions or any feedback that you guys have.